whenever you have these questions about speed, you want to see which speed do they want. Remember, we have average velocity, mean free path velocity, and root mean squared velocity. So when you read the question, you want to use the right equation if it's asking for a specific gas. For this one, though, we're going to write down our equation for this, which is the square root of 8RT over pi times the molecular mass. So you'll notice that this equation, we have a lot of constants for this. We know all the gases are going to have the same temperature. They're all at 0 degrees Celsius. They're all going to have the same gas constant, which for this one it's 8.314, not 0.08206. All of them we're multiplying by 8, and we're all dividing by pi. So this equation, for this question, and for this equation, it's always a function of the molecular mass of the gas you're using. So if we can treat these variables as just being 1, we're going to make them go away. We can think of this equation as being simply just the square root of 1 over the molecular mass. So if we arrange our gases from lowest molecular mass to highest molecular mass, then we can automatically determine which one's going to be the fastest and which one's going to be the slowest. We won't have numerical values for them, but we can arrange them from slowest to fastest. So the molecular mass for helium is 4. So that's definitely going to be our lowest. I'm arranging from lowest molecular mass to highest molecular mass. The next gas on the list is going to be methane. After that, we have ammonia, and finally we have chlorine gas. So this average velocity is equivalent to 1 over the molecular mass. So the larger this number becomes, the smaller this number becomes. So they're inversely proportional. So if I were to arrange these from slowest, so this is molecular mass, if I were to arrange these from slowest molecule to fastest molecule, you'll notice it's just going to be flipped. Our heaviest molecule, based on molecular mass, is going to be chlorine, so that's going to be the slowest one. Next up on the list is ammonia, then methane, and then helium. So this is arranging in speed. The heavier something is, the slower it will travel through space. The lighter something is, the faster it will travel through space. Little skinny thing, go real quick. Big bulky thing, go nice and slow. That's really as complicated as it gets. So that was for this first one. For which do the molecules have the highest average velocity? I'm gonna take this off and put a clean one so we can do the second one. Next question says, for which gas are collisions elastic? Well, when we were talking about the kinetic theory of gases, we said all gases are elastic. They have to be elastic for this theory to work. So all of them, helium, chlorine, methane, and ammonia, are going to have elastic collisions in their container. Not one of them is going to be more than the other. They're just all going to be treated as they're elastic. And then finally, which gas has the lowest kinetic energy? Well, our kinetic energy equation is EK is equal to 3/2 RT. 3/2 RT. Dan, do you have the really quick?
What do you mean?
The equation for here we go. For kinetic energy. Let's find it really quick. It should. I always forget if it's 3/2 or if it's 2/3.
Or average.
For just kinetic energy. I found it. I did have it right. 3/2 RT. There's no molecular mass in this at all. It's just a function of temperature. So all of these are going to have the same kinetic energy. None of them, not one of them is going to have a lower kinetic energy than the other. They all average out to be the same. Okay. Yeah, I can remember if it was 2/3, if it was 3/2. I think I'm dyslexic, man. Dan's saying this. He's like, yes, you are. You're very dyslexic. Example number 8. Calculate the following ratios for a gas at Kelvin temperatures T1 and T2, where T2 is equal 2 times T1. The effusion rate ratio is going to be T1 to the T2 effusion rate. So effusion rate, I have to grab the book because it's actually in the book, which is great. Let's find effusion rate really quick. Yes. Effusion rate is going to be, let's see if I can zoom in on this. Right there. It's going to be a function of molecular masses, square root of molecular mass of one gas to the other gas. So what we're going to do is we're going to do a ratio of the two temperatures. So it's going to be the diffusion rate of the gas at one temperature and then that same gas for another temperature. So we want to know, it's going to be T1 over T2. Whoa. Okay, there we go. And this ratio, this diffusion is always going to be the square root of one over the other. We know that T2 is going to be 2 times T1. So our T1s essentially cancel out. And so if you were to plug 100 Kelvin here and 100 Kelvin here, then what we're left with is going to be 1 over 2, the square root of 1 over 2. This ratio value is just going to be 0.707. That's the answer. So it doesn't matter what temperature you plug into it, you're going to get the same ratio because of the fact that T2 is 2 times T1. So this ratio just kind of doesn't matter what temperature you plug into it. And that concludes all gas examples. Okay. Move on to example number 9. So now we're starting quantum. We're going to start with some wavelength calculations. Granted, this one doesn't necessarily have any, you don't have to do any math, you can just look at it. And let's do it like that. Okay. Which of the following frequencies correspond to light with the longest wavelength? So you'll recall that the relationship for frequency and wavelength is C is equal to lambda times nu. So wavelength is inversely proportional to frequency, meaning that the larger this number becomes, the smaller this number becomes. So if our frequency was extremely high, let's say for C, this is going to have the shortest wavelength because it is the largest number of the 5 options you can choose here. So we want to find the longest wavelength where this is small. It's a small number instead of a really big number. So then we have 9.12 times 10 to the 12th, 3.2 times 10 to the 9th, 8.5 times 10 to the 20th, 3 times 10 to the 13th, and then here we have 4.12 times 10 to the 5th. This is the smallest magnitude of frequency. So our longest wavelength is going to be this one. Right on my paper. Because it has the smallest frequency. Small frequency means long wavelength. High frequency means short wavelength. They are inversely proportional. Light has a wavelength of 5.6 times 10 to the second nanometers. What is the energy of this photon of light? So we know that our energy equation is going to be equal to H equals H nu. So you can do this question two different ways. You can change your wavelength to frequency and plug it into this equation, or you could just simply use this equation. Equals H nu, E also equals H times C over lambda. So all we did is our relationship for C equals lambda times nu. We rearranged this to solve for nu and plugged in the expression into this equation. That's how we get this relationship right here. So this is just a plug and chug. H is a constant. It is given to you in the back of the exam. It is 6.626 times 10 to the negative 34th joule seconds, not joules per second, joules seconds. C is the speed of light, which is a constant, which is going to be 2.9979 times 10 to the 8th meters per second, over our wavelength, which for here is 5.6 times 10 to the second nanometers. This has to be in meters. If we plug this in as nanometers, we're going to get an energy value that makes no sense. When you convert this number from nanometers to meters, you get 5.6 times 10 to the negative 7th meters, giving you an energy value of 3.55 times 10 to the negative 19th joules. So this is the energy of one photon of light. So like I said, you can change your wavelength into frequency and plug it into here. You can just plug it into here, just as I did, and get exactly the same answer. Saves time. I would do it my way simply because in a test with so many questions this is a fairly simple one. You want to get through it as quickly as possible. Here is a de Broglie question. Joy. Not that. Not that either. Consider an atom traveling at 1% of the speed of light. The de Broglie wavelength is found to be 3.31 times 10 to the negative 3rd picometers. Which element is this? There was a question in your homework that was very, very similar to this, actually. So de Broglie wavelength is going to be equal to Planck's constant over m times c. We're going to solve for m here. Once we solve for m, we're going to go from the mass of one atom and using Avogadro's number go to a mole of atoms. And that's going to give us our molecular mass. You'll see how the math works out in a second. So I'm going to rearrange this equation so I'm solving for m here. So I'm going to multiply both sides by m, and then I'm going to move this lambda down here by dividing both sides. M is equal to h over lambda c. Let's convert, or I'll actually convert the picometers to meters. Our units have to be in meters in order for the units to cancel out properly. So I'm going to convert 3.31 times 10 to the negative 3rd picometers to meters. There are, in 1 meter, there are 1 times 10 to the 12th picometers. So if you, there should be a handy dandy conversion in your textbooks. This is a different textbook, but all textbooks should have a table that shows how you can go from one unit of measurement to another unit of measurement. Give me a second while I look for it. Oh man, maybe this one doesn't have it. Don't let me down. Like panicking up here because I feel like I'm wasting time, but I forget this is just a video. So if you know what this is, you can just fast forward through this until I get to the part where I'm actually actually like stopping for
For H.
it. Huh?
H.
No. I'm like trying. I want to show the relationship of picometers to nanometers to meters, because picometers is something that they don't really use. Okay, here we have there we go. That's what I was looking for. SI units. Move this up. If you can see that. Here we go. So pico is going to be 10 times negative 12. It's three orders of magnitude off of nano. Milli is negative 3, micro is negative 6, nano is negative 9. Pico is just the next step down. So that's where we get that conversion from. This right now. So now. Okay. So this gives us a value of 3. Where's 3? 3.31 times 10 to the negative 15th meters. So now I'm going to plug my meters into my wavelength. C is a constant, H is a constant. So the mass of one atom is going to be 6.626 times 10 to the negative 34th joule seconds over my wavelength, which I just calculated was 3.31 times 10 to the negative 15th meters. Do that. Times C, which is the speed of light, 2.9979 times 10 to the 8th meters per second. This is going to give me a mass of 6.68 times 10 to the negative 26 kilograms. And the reason it's kilograms and not grams is because in a joule it is kilograms meters squared per second squared. So if you were to actually write down the units, the SI units for a joule, everything will cancel out and you'll be left with just kilograms. Okay, so we have our mass. I'm going to move the question out of the way and finish doing the math of this. So this is the mass of one atom in kilograms. We want our units to be grams per mole. This is our end goal right here. So what we're going to do first is we have to convert our kilograms to grams. And we can get a mole from just Avogadro's number, because Avogadro's number is going to be 6.022 times 10 to the 23rd objects per mole. That will give us the correct units. So we're going to do some stoichiometry here. 6.68 times 10 to the negative 26 kilograms. And I'm going to move to blue because this pen is starting to I've moved it. In 1 kilogram has 1,000 grams. And Avogadro's number is going to be 6.022 times 10 to the 23rd atoms per mole. That's going to give us, so you'll see the kilograms cancel out here, you'll be left with grams. And then you'll be left with grams per mole. The math of when you plug this into the calculator, you get 40.2 grams per mole. And if you go to your periodic table, the element that has that molar mass, if I can zoom in, is calcium. Calcium is 40.078. So this is close enough to tell us that the element we're looking at is going to be calcium. Oh, I did not do a step. Do you see the error? I skipped one step.
Oh, grams to moles.
No, I skipped one step. I'm glad I caught myself too. There would be a student right now waving their hand like this saying, that ain't right. If you look at the question, 1% of the speed of light. I multiply this by 2.9, 100% of the speed of light. So what you do is, sorry, I apologize for this. This is the correct answer. I just forgot to insert a step right here. That's what I get for rushing through things. This is going to be 2.9979 times 10 to the 8th meters per second times 0.01, because it has to be 1% of this speed. I completely forgot to do that, and for that I am very sorry. So don't forget to multiply. If you multiply this by 0.01, which is the fractional version of 1%, you get the correct answer. You get this amount of mass for one atom, and then you convert to give you 40.2 grams per mole. There was a question on the homework that was very, very similar to that, and that's where people got tripped up was, I don't understand what this 1% means. Basically, all it means is you take your C and you multiply it by 0.01. That's it. Okay. Well, I botched that one. Done goofed. So that was example 11. Let's try not to goof anymore. There's already been enough goofing. Example 12. What is the wavelength of light that is emitted when an excited electron in a hydrogen atom falls from the n equals 5 level to the n equals 2 level? This is a Rydberg equation question. So the energy of an electron moving orbital levels is going to be equal to the Rydberg constant times 1 over Ni squared minus 1 over Nf squared. Somebody pointed out to me that the way the textbook has this written has a negative in front of the RH. The reason it's in front of that is because these are switched. So if it's n of the final minus the n of the initial, then you put a negative in front of this R sub h, and then it'll still give you the right answer. It was the same mistake I made when I put a negative in front of it, because I was thinking of the other way. So, sorry. So Rydberg's constant, which is going to be given to you in the exam, is 2.178 times 10 to the negative 18th joules. We're going from n equals 5, not z squared, to n equals 2. And z squared is the atomic number of our element. We're dealing with hydrogen, so this is just going to be 1 squared, which is just 1. So I'm not even going to bother putting it there. We're just it's invisible, it's there. Remember, we're lazy, we don't like writing things in. Our energy is going to be equal to negative 4.57 times 10 to the negative 19th. Remember, it's saying emitted. When something is emitted, this energy is going to be a negative value. When something is absorbed, this value is going to be positive. So if you read a question that says emitted and you get a positive value in here, you probably have these two flipped. And if you are absorbing something and you get a negative value, again, you probably have something flipped in here. Or you accidentally put a negative sign in front of it, or go back and make sure that you're using the right equation. So we want to know the wavelength of this, the light that's being emitted as this electron falls from n equals 5 to n equals 2. It's going to release a photon. So E is equal to hc over lambda. And we're going to rearrange this equation so that we're solving for lambda here. So I'm going to divide both sides by E, and I'm going to multiply both sides by lambda. So lambda is going to be equal to hc over E. And all we do here now is we just plug and chug. H is a constant, it's our Planck's constant. C is our speed of light, and E is what we just solved for. When you plug your E value in here, take the absolute value. Don't plug in the negative, because you can't get a negative wavelength. That makes no sense. Planck's constant. 2.9979 times 10 to the 8th meters per second. all over, or E, which we just calculated was 4.57 times 10 to the negative 18th joules. I'm going to move this like out of the way. So our lambda, our wavelength is 4.35 times 10 to the negative 7th meters. You can see that as the units, our joules cancel out, and our seconds cancel out, we're left with meters. Okay, what was example 12? Moving on. We have 3 more. Well, 2 more, because we're 13 right now. What is the probability of finding a particle in a one-dimensional box and energy level equals energy levels n equals 4 between x of L over 4 and x of L over 2? L is the length of the box. This question is a mouthful and can scare, well, I mean, the utter life out of somebody. The first thing you want to do when you're asked a question like this is we want to draw the wave function. Dan, I'm like making sure I don't mess this up, because Dan is a quantum chemist and he's like judging me. I'm like walking on eggshells right now, man. Am I doing it right?
So far.
So far. It's acceptable. So here's our box of size L. We're doing size sub 4. So it's going to have 4 humps. And remember, this is a sine function, so we're starting at 0. It's not a cosine function. This is going to look a little wonky. 1, 2, 3. There we go. 1, 2, 3, 4. And we want to look at, so if we think about this particle being in this box, if I were to ask you, what is the chances of the particle existing from 0 to L? It is 100%, because it's going to be in the box. It's bouncing back and forth forever. And if I were to ask you, what's the chances that the particle's in the box? You say, well, it's 100%. It's bouncing back in there forever. Yeah. But if I were to ask you, what are the chances you're going to find it in this portion of the box? Then what you do is we're just going to look at a certain length. So from here to L is a full length of L. So we're looking from L over 4, which is a quarter length of the box, to half the box. So a quarter of the length would be right here. So this is L over 4 to here, L over 2. It's not drawn to scale, so Dan's judging me so hard right now. So if the entire box, if you look at the entire box, it has a 100% chance of being inside the box, then a quarter of that would just be a quarter of 100%. So the chance we're going to find it is going to be 100% times 0.25, which gives you 25%. So the chances of finding this particle that's going back and forth in this window in the box is simply just 25%. And for the fun of it, let's write down the equation for this wave function. So the generalized form of this equation will be given to you in the back of the exam. We have psi sub n is equal to 2 over L sine of n pi x over L. So all you would do is, we're looking at 4, so this becomes 4, and this becomes 4, and then you're done. And then if you wanted to do the probability function, then you would just square this entire thing. Square root would go away, you would get 2 over L, and you would get sine squared 4 pi x over L. You don't square the stuff that's in here, you only square the trigonometric function. Okay. Dana's still judging me. All right. Quantum numbers. What time is it?
It is 12